Alright, so in between the last video and now, I went ahead and added all of the method stubs, and I also included the size method because I realized that in the uh, diagram here I did not have a method for getting the size, but of course that would be something that's very important to have. And I also decided that if we're going to write tests for this, we can actually we can do two things. One, or rather I realized one thing and we did something else. The first thing is we can just reuse all of the code from the mini array list example and just uh, change the the mini array list to singly linked list. We do not need the doubling factor test because there's no resizing here. But secondly, I realized that we should just do the bounds checking anyway because that makes all of these tests work. So we're just going to add the code very quickly to do these bounds checks. Okay, so and in fact we can just copy the bounds checks from the existing methods in the mini array list class. Okay, so this will actually be an optional instead of just t, and we'll change all these to index rather than size to be consistent. So the only thing we're changing here, the only thing that we're going to do differently is the code that goes inside of the these methods here. So, and that's very broad, I just realized. What I'm saying is that the bounds check stays the same. The code that changes is the actual, like, what interfaces with the underlying mechanism. So remember that with an array, or with an array list, we interface with this elements array, and we have to resize. But if we don't have an array, then there's nothing to resize, right? The only thing we have to do is just adjust pointers, right? Adjust links. So let's finish this, and then we'll get started. Okay, very good. So that's not going to compile for the moment, or for the time being, but that's fine. So we first need to create our constructor, of course, and the constructor is very straightforward. We're just going to instantiate this dot first to be null, this dot last to be null, and then this dot size to be 0. And one thing that you see in the book actually is that you can combine these assignments here into one. And the reason why you can do this is because remember, this is the assignment expression, and we talked about this very briefly, but assignment is right associative, and what that means is that it's actually looking something like this. So it first assigns null into this dot first, and then the result of this dot first gets assigned to this dot last. So it's just saying assign both of these to be null, and yeah, but we'll make it very clear for this video. Okay, so how is this going to work? How are we going to add something into our singly linked list? Well, there's two cases here. The first case is if the list is empty. How do we add something to an empty list? Well, the thing that we add, of course, will be a new node. Let's say we want to add the value 5. Okay, so this is now the first thing, and it's also the last thing, right? And the thing that is added is, of course, going to be null. Okay? So, or the next pointer is going to be null. So this is actually a very simple case. And we're going to coalesce, or combine, not coalesce. We're going to combine these two cases into one. Or rather, we're going to minimize as much redundant code as we can by combining some of these clauses here. Okay, but now let's say we have a non-empty list. So we have some values v, and then maybe some other stuff. And what we want is to add the value, let's say the value 5, and then the next thing will of course be null. So this is the first thing in the list. And then let's say we had some, so maybe the dot 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 wasn't the right idea here, but let's say that this has, let's say that this thing that I'm drawing right now was the was the previous last thing in the list. So let's say the last element was 10, and then this thing points to the new thing, or rather, this is going to be the resulting list. So right now, this is the last element in the singly linked list. And what we want to do is update two things. We want to update the previous last pointer, the previous last next pointer, so this thing, we want it to no longer be null, because remember, before we add this 5 here, that's going to be null, right? Because it has to be. So right now, this points to null. We want to say, take the new node, make the previous last thing to point to it, and then, let me fix my webcam here, there we go. And then we want to say, make the, let's see, there we go. And then make the new node's next pointer be null, but that's already that would already be handled by the constructor. But then we want to say, make this not be the last, but this new thing will be the last. Okay? So we have this operation. So last.next equals, we'll say this new node is n. So up here we're going to say first is equal to n, but then in both cases we're going to say last is equal to n. And the reason why is because here we would say last is equal to n because when the list is empty, the first thing we add is also definitionally the last thing, so we have to have this here. But then here we have to say, or at least in this case down here, case 2, we have to say, well, when the list is empty, or when the list is not empty, then we have to update the thing that was the last is no longer the last thing because we just added something to the end of it. So whatever we just added is the new last element of the list. Okay, so it sounds like a lot, but it's not too bad. So, right. So we'll handle this. We'll actually handle insertions differently from additions. We won't. We'll have a little bit of duplicate code, but that's fine. So we'll actually copy and paste both of these here. So this will never return false because we're always adding onto the end. But we have to first say if the list is empty, and if it's not. And in either case, we'll return true. So if it's empty, well, the first thing we're going to do is we're going to create a node, and we'll just call that n to be consistent with our diagram. This is going to be a new node whose value is v, and whose next pointer is null, and we know that because of how the method, or the constructor, one of the constructors, is defined. Okay? So if the size is 0, so if the list is empty, we'll say this dot first is equal to n, and then down here at the bottom, we'll do this dot last, or rather, let's do it all in one. So this dot last is equal to n, and then this dot size plus plus, and we'll also put the return true in here because I want to show you how we can refactor this. Okay? So what if it's not empty? Well, then we want to say this dot last dot next is equal to n. Okay? So whatever was the or whatever is currently the last, its pointer must be null by definition. But now we're saying we want that pointer's next to point to the new thing we're adding. Okay? And then we're going to say the last thing is now going to be n. So this really requires a strong understanding of how aliasing works and how mutation works. So if you're confused as to why this doesn't overwrite the existing node here, like why doesn't that like just outright remove 10, then you really need to draw this out and go back and rewatch or reread the mutation and aliasing videos, because this is very, very fundamental to how this works. Okay? So then we'll say this dot size plus plus and then return true. But notice that there's 3 duplicate lines of code here that always execute. So we can just move these to outside of the if statement. Okay? So that's insertions to the rear. Okay? So let's jump down to get. I think get's very simple. So what we're going to do is, well, actually get is not that simple. So what we're going to do is we're going to first start off by saying we're going to have a current node, and that's going to be equal to this dot first. So then we're going to say for int I equals 0, I is less than the index, I plus plus. Now, the question is, how do we traverse through this list? What we can do is just say cur node is equal to cur node dot next. And we can do that because what this is doing is it's saying, okay, if we're on the first thing in the list, for example, we have this, and then we have this, then we have this, then we have this, and let's say this points there, this points there, this points there. So if cur node, we'll just abbreviate it as C, is pointing to this, then its next node must be this thing. So each time through the loop, as long as I is less than index, then we're going to say that C just becomes the next thing in the list. So that means that now C will move over to here, and then it will move over to here, and then down to here, and then wherever it needs to go until we get to the node that we're on. So, for example, if I is equal to, or if index is equal to 2, then we're going to say when I equals 0, we're going to move it to here, increment I, and then we're going to say we're going to do it again because I is less than, because 1's less than 2. So then we do it again, but now 2 is not less than 2, so we're done. And then, now that we're on this node, we can just do C dot value to get its value. Okay, so if this value is 3, then this is 10, and this is negative 7, then C dot value is equal to negative 7. Okay, so that's all we gotta do. And then we can just do return cur node dot value. Okay, or well, we need to wrap it in an optional because we have to, and we're done. Okay, so setting is also just as simple. All we have to do is say, just loop through, and then we're going to say cur node dot value, value equals v, because all we're doing is we're just doing the same thing. Go to the node and then change its value. So let's say we want to change the value at index 2 to be 400. All we do, we hop, overwrite this from negative 7 to be 400, and then we are done. Okay, so cur.value equals 400, and then we're done. Okay, the link doesn't change, which is what's good about this. Okay, now we have insertions and removal. So this is probably the trickiest part by far. So insertions, at least, is we have a couple cases. The first case is, so case 1, when the list, or rather when the index, when index is equal to 0. When we insert at index 0, we're inserting at the front. So what that means is we need to say that we have a new node in. So this thing must become the first, right? Because if we're inserting at the front, then it's definitionally the first thing in the list. Okay? So to do that, we need to say that in.next is equal to the old first, and then say then say first is equal to n. So whatever the first thing previously was, set n's next to point to it. So if we're saying, if we have a list of 5 and then it has some other stuff, we want to add a 20 to the front, then its next must be the old first. But now this thing must be the first thing. Okay? And then we say size plus plus. Okay? So let's write that case first. Okay? So if index is equal to 0, then we say this dot, or rather, let's first create the node. There we go. So we'll say this dot, or rather, in dot next is equal to this dot first, and then this dot first is equal to n, and then we're done. Okay, so again, this code is going to be synonymous in all branches, so we'll just keep it the same. So now we need to know, what if the node is equal to the last thing in the list? So, or not the node, sorry. What if the index is equal to the size? Rather, that means, what if we're inserting at the next index in the list. Well, what we could do is actually just call this method right here, because that's effectively what we're doing. So if index is equal to, let's see, index is equal to this dot size, then just return this dot add with the value v. So what that means is actually we've created this node twice here. So, but it doesn't matter. The node will just get scooped up by the garbage collector. So it's also important to note that this n and this n are not the same n. They're completely different nodes, just with the same name. But remember that the scope of a variable, at least in this, like with the same name, is only within the braces that is defined. Okay. So what if it's not one of those cases? What if it's one of the harder cases? So if it's one of the harder cases, that means that we're trying to insert. That means we have some node, like let's say 5, and then some node, let's say some stuff here, and then we have some node at the end. So there's at least one node in front and one node behind. Okay? And we're wanting to insert, let's say, right here. So what do? We need to say that the new node, or rather, we need to do one thing. We need to get the node that was previously behind it, set its next pointer to not point to whatever was here before. Like let's say, this is a bad drawing, so let's restart it. So we have a node here, we have a node here, so 5 and then let's say 3. So the 5 points to the 3 points to nothing. Okay. If we're inserting a node in between these, let's draw it like this. Let's say we want to insert 10. We want the 5 to point to, not to the 3, but rather to the 10. Okay. We want the 5 to point to the 10. Okay. But we want the 10 to point to the 3. Okay. So this is our n. Okay. But the question is, how do we get this node right here? Well, all we have to do is just loop n minus 1 times, where n is the current index. And interestingly enough, we can use our get method to do that. So what we'll do, actually, no, we can't. Sorry. We cannot use our get method because it does not return a node. It returns the value, so we can't do that. We'll have to do the loop ourselves. But that's not very hard. All we have to do is just say node t, we'll say previous equals this dot first, for int I equals 0, I is less than index minus 1, I plus plus, previous equals previous dot next. Okay? Now that we have that, we now know what this index, or what the node is at this index. Now there could be stuff before this, right? There could be some stuff over here. There could be a whole bunch of stuff. But if we're trying to insert, like let's say that this is index 4, this is index 5. If we're inserting at index 5, then this is going to be the new index 5. Okay? So we'll actually loop to get us index 4, to get us the node at index 4. Okay? And we'll say that the value at index 4 is going to, or the node at index 4 is going to point to, its next pointer is going to point to our new node. And then the new node's next is going to point to the thing that 4 was previously pointing to. Okay? So we'll say that this is m, and we'll say that this is p for previous. So we'll just say prev, and we'll say m for, I don't know, something. Okay? Or let's be a little bit better. Let's use better names here. Let's say this is old next. Okay? So old next is equal to what? It's equal to previous dot next. Okay? So remember, if this is previous, then right now it points to the old next. It has to, by definition. We haven't inserted this yet. This is all post insertion. Okay? Now, we're going to say priv.next is equal to n. Okay? That establishes this link right here. This link right here. Okay? So we've just hooked up this node. We detached the old link that was here. That's no longer there. Okay? Very good. So now what? And also, it's important to, the reason why we have to save it here is because we overwrite it in the very next operation. So we have to save it. If we don't save it, then we have no way of getting access to it. Okay? So now we're going to say in.next is equal to the old next. Okay? And then that's it. So it's like we're doing a temporary variable assignment here. It's kind of, and in fact, if you look at this kind of, squint your eyes a little bit and look at it, this is almost like we're swapping variables. Okay? But it's a little bit more convoluted than that. So you'll have to really kind of just stare at this and maybe it'll eventually click. Okay? So let's actually run some tests. We haven't ran anything yet, but let's run the get test to see if this works. It does not because this does not compile. So we'll just say, let's say for now, just throw new error to do. Okay, so let's run this test, and the get works, which is nice. The size should work. It does not. Remove, of course. I forgot that test remove. If we don't test remove, it works just fine. Let's not test remove. Let's test set. Set works perfectly. Add and insert both work, or all work perfectly. Okay, so we're 21 minutes in, but let's do remove now. Remove is also actually not that hard. It's actually very similar to insertion, okay? Except we're just removing something and not inserting something, okay? So how do we remove something? Well, again, we have three cases, okay? If we're trying to remove from an empty list, we obviously that is caught by this if statement here. We can't remove from an empty list, otherwise this would be true, okay? So what do we do now? Well, again, we have a few cases. So case one, what if we're removing the first element? Okay, so what do I mean by that? Well, I mean, hopefully that's pretty clear, but let's say we have a list 5, and then 30, and then something else, whatever. Well, what we're doing is we're going to say, this is actually very straightforward. All we have to do is just say, if this is the first, it's not going to be the first anymore. The first is now going to be the thing that first is pointing to. So all we have to do is just say that first is equal to first dot next. Okay? And then that effectively delinks this from the linked list. It doesn't actually remove anything, but since nothing is pointing to it anymore, then it will just get garbage collected by the garbage collector. Okay? And in any case, we're going to first get the value. We'll set that to be null, and then we're going to decrement the size by 1 and return an optional of the value that we're removing. Okay? So we'll set to null for now. We'll do some stuff, and then we'll decrement the size, and then we'll return the optional with the value. Okay? So if the index is equal to 0, then that means we're removing the first thing in the list. Okay? So we'll say, we'll first get the value that's at the first. So we'll say value is equal to this dot first dot value, and then we'll update the link. So this dot first is equal to this dot first dot next, and then we're done. Okay? So that's case 1. Case 1 is pretty easy. So what is case 2? Case 2 is probably, as you might have guessed, is removing the last thing. Removing the last thing in the list. Okay? So this is actually also, well, this is slightly harder because we're going to have to get the thing that is right before the last and set its pointer to be null. So let's say we have a list with some pointers, and then we have like a 5 here, and then we have, let's say, a 3. But if we're removing the 3, like let's say that this is the last, we're going to have to search for the thing that is the second last in the list. Okay, so this is the second last. So we're going to have to search for the thing that is at index -1, and then set its next pointer to instead be null. And therefore, there is there's going to be two things. We're going to set its next pointer to be null, and then we're going to say that this is now the last thing in the list. Okay? So we have to get rid of this link, and we have to get rid of the fact that last is now pointing to the second last thing. Okay? So that will mean that there are no references to it, and that will get it collected by the garbage collector. Okay? So again, this is going to be a for loop. So else if this dot size is if this dot or index is equal to this dot size minus 1, then we'll say node second last is equal to this dot first for int I equals 0, I is less than index minus 1, I plus plus, second last equals second last dot next. You're noticing a theme here. Okay, and now we do the two steps. We say second last dot next is equal to null. This dot last is equal to second last. And that's it. Okay? But now we have the hard part. What if we're removing something that's in the middle of a list? So we have some stuff here, or let's say we have some stuff before. There's some pointer here. We have, let's say, a 5. Let's say we have a 3. And then let's say we have a 10. Okay? And then maybe there's some stuff after it. We don't know. We don't care. Okay? We want to remove the 3. Well, as you can probably kind of guess here, we're going to have to get the previous thing in the list. But this is actually where it's simple. I mean, we know how to do that. Of course, that's just index minus 1. But all we have to do here is just say, well, just update its next pointer to point to the thing that we were looking at, or the thing that we want to remove. We want to get the thing that we want to remove, which is just the previous is next. Of course, that's just this. And previous.next.next is this thing, right? It has to be, by definition. So all we have to do is just say previous.next. This is getting a little convoluted, but if you just study the diagram, I think it makes more sense. We'll say previous.next is equal to previous.next.next. Okay? So it doesn't point to this thing anymore. It now points to, rather, this link is no longer established. Okay? So we'll mark through that with red. It now points to this thing over here. Okay? That's what this line does. It unhooks it from the thing we're removing, and then it hooks it to the thing that we're going to, we want it to now point to. Okay? So that means that this now gets garbage collected, and we're done. Okay? So, for the third time now, let's just copy our loop. We'll say previous to be consistent here. And then we'll say previous.next is equal to previous.next.next. Now you may be wondering, well, how do we know that all of these values even exist? Well, we know they exist because if they didn't exist, they would have been caught by one of these. Okay? There has to be at least 3 values in the list there has to be at least 2 values in the list for this to even occur. Okay? But if there are only 2 things in the list, then one of these would actually be captured. So actually, no, I was right. There do have to be at least 3 things in the list for this to happen. But either one of these could actually be, there could be just one thing. So we could be removing the first thing, or the last thing, or something in the middle. Okay? Okay, so let's test all of these now, and everything should work. Okay, it does not work, so we get a null pointer exception. So, it's because I'm not setting the, I'm not actually getting the value that we want here. So, let's see. So, we first have to do the following. So, if we're removing the last thing in the list, then we're going to have to say that, let's see. So the value that we're going to remove is the last thing in the list. So we're going to have to say the value is equal to this dot last dot value. Okay, so we can do that either before or after this statement here. It doesn't matter. And now the thing that we're going to do here is we're going to say that the thing we're removing here is previous dot next, right? That's the thing we want to remove. Okay, so we'll say the value is equal to prev dot next dot value. Okay, and now all the tests pass. Okay, so this code is pretty convoluted to understand. I completely agree, and I'm sure there are better ways to optimize this, but these are the general things that you have to do when implementing a singly linked list. And the big thing here is having a private static class that is a node that represents the underlying data of the linked list. Remember, the underlying data for the mini array list was an array. For a linked list, it's a bunch of nodes. Okay, so study this code, retype out this code, run through the debugger, draw it out with images, do whatever you need to do to understand this, because this is extremely important, and knowing how this works will really help you get through the final question on problem set 4.